Hello, in this video I'll be explaining about matrices and their properties. First of all, what is a matrix? An M cross N matrix A is rectangular array of elements Aij placed in M rows and N columns. That is given by Aij has, like, if you see, it's arranged in M rows and N columns. And if the number of rows are equal to the number of columns, then it is called a square matrix. These are the examples of a 2 cross 2 matrix and a 3 cross 3 matrix. A square matrix is called a symmetric matrix if the elements of the matrix are symmetrical along the main diagonal following the green path. A square matrix is called a skew symmetric matrix if Aij is equal to negative of Aij. That is, like, let us consider the 3 by 3 matrix 0 to minus 5 minus 2 0 minus 4 5 4 0, and its change, like the complete opposite. Minus a would be 0 minus 2 5, and if you observe it closely, this is also equal to the A transpose. So a square matrix is called a skew symmetric matrix when the negative of the original matrix is equivalent to the transpose of the matrix. A square matrix is called a diagonal matrix if all elements outside the main diagonals are 0. And the main diagonal is non-zero. And a diagonal matrix is called identity matrix if all the elements on the main diagonal are ones. A zero matrix or a null matrix has all zero elements. Matrix A is equivalent to matrix B only when the number of rows in each matrix are equal to the number of columns in the other matrix. That is, a m cross n is equal to m cross n of A and B, and all the elements are equal, not just the size. Addition of matrices. Let us consider these two matrices, 2 by 2 matrix A, B, C, D, E, F, G, H, and these are the addition of a matrix is performed element wise. A plus E and B plus F, C plus G, and D plus H. Subtraction of matrix is performed similar to the addition. Matrix multiplication by a constant. When we multiply a constant k to a matrix A, we have to multiply the constant with each element, that is Ka, Kb, Kc, and Kd. And coming to the matrix multiplication, the product of two matrices A and B exists if and only if the number of columns in the matrix A is equal to the number of rows in B. For example, let us consider this matrix A1 1 1 2 1 3. In this, if we observe, we see it has 2 rows and 3 columns. And similarly, in the matrix B, it has 3 rows and 1 column. And carefully, if we observe, the number of columns in matrix A is equal to the number of rows in B. So this yields 2 cross 1 matrix with 2 rows and 1 column. Transpose of a matrix. The transpose of a matrix is obtained by interchanging rows and columns. So A, B, C, D, E, F, G, H, I, changing them, the entire column becomes a row. A square matrix is called orthogonal if the product of its original matrix and the transpose of it is equivalent to an identity matrix. And with the same property, when two matrices are multiplied and a transpose is taken of the product, it is equivalent to the product of transpose of the matrices in the reverse order, B transpose times A transpose. the adjoint of a matrix. If A is a square matrix of order n, it can be 2 cross 2, 3 cross 3, and so on, then the corresponding adjoint matrix A strict is formed by the cofactors of Aij of the elements of the transposed matrix A transpose. Let us consider this example. We have an 3 by 3 matrix A B C D E F G H I, and before we do that, let us see the pattern of minor. So this is empirical, and these are the signs which are followed in a 3 by 3 matrix. So please pay attention to this, and this actually plays a key role in while multiplying and making any calculations. So once we have the minor, we apply that here, and then we take the cofactors of A. So that is, for the cofactor of the first row and first column would be the elements of these here, and then similarly for B it would be DG and FI, and for C it would be DE and GH. So for if we are considering a particular element in a row and a column, we have to ignore the entire row and column. So if we are considering A, so the entire first row and first column ignored, and the remaining elements of in the matrix are considered for the cofactors. And once we construct the cofactor matrix and the determinants are calculated, then we perform a transpose. And after performing the transpose, this gives rise to the adjoint matrix of A. If A is a square matrix of order n, then its trace, denoted as TR parenthesis A, is the sum of the diagonal elements, that is A, E, and I. Just the sum of the principal diagonal. Inverse of a matrix. For a non-singular square matrix whose determinant is non-zero, its inverse is given by A inverse is the adjoint matrix divided by the determinant of A. And we know how to calculate the adjoint of the matrix from here. So once we calculate the minor cofactors and take a transpose of the cofactors, we have the adjoint, and then we calculate the determinant of A, and once we have it, we just use this formula to calculate the sorry we use this formula for a and of a dimension n. So for example, if it is a 2 cross 2 matrix like similar to ABCD, and it's relatively simple to the compared to A 3 cross 3, so because we have to just like interchange the elements in the principal diagonal and then flip the signs in the other dimension. So we can obtain an A inverse for a 2 cross 2 by using this formula, but for a 3 cross 3 matrix we have to use the adjoint and then divide it by the determinant A. And one of the important properties of the inverse of a matrix is when A is multiplied by A inverse, it gives rise to its inverse, an identity matrix. So that is, all the principal elements on the diagonal matrix would be 1, and then even in the order in which it is performed, either it is A into A inverse or A inverse into A, it always gives an identity matrix. And these are few properties of the matrix products, the product of two matrices and the inverse is equivalent to the product of inverse of matrices in the flip positions like B inverse and A. But the opposite is not true. AB inverse is not equal to A inverse and B inverse. So, and another property is when we take a transpose of a matrix and the determinant is calculated, it is still equivalent to the A transpose. Oh, little correction. This is what I meant to say. The determin the de- sorry. Yes, the determinant of a transpose of a square matrix is equivalent to the determinant of the original matrix. That is, like, let us consider a matrix A is B, C, D, and the transpose of this would be AC and BD. Determinant of A transpose is AD minus BC, and the original determinant would be still AD minus BC. So this is the property. And by reordering the rows and columns in a determinant, the sign of the determinant is changed. So if we calculate the determinant A, B, C, D, and if we flip the rows and columns, the entire row is shifted. Then we have to place a negative sign. It would be equivalent to the negative of it. And if any row or column is repeated in a square matrix, then the determinant will always be 0. And if we multiply a constant that which is the same number is multiplied to any particular row or column, it is equivalent to multiplying the determinant by that number. So let's see. So we have the determinant would be Ka into D minus KBC, that is equivalent to K into AD minus BC, KD minus KBC. And in similar way, the linear combination of elements of a determinant, if the elements of any row or column is multiplied by a constant factor K, or multiplied by a constant factor and added to the corresponding elements of the row or column, then the value of the determinant doesn't change. Like if we calculate, it would be A1 plus KB into D minus C plus KD into B. This is just A. This is AD minus BC, and this one window is AD minus BC. So these are some unique properties of the determinant and some properties of the matrices, which I think would be useful as a refresher for this course. If you have any questions, or if you think that I haven't covered enough, or if you still need some more information, please let me know, and I will make sure that in one of my upcoming videos I will upload that. Thank you.